Okay, hi everyone. So we're going to start this. We're going to give this a session on what's new in C# 9. I'm going to concentrate actually mostly on the very last thing in this, which is the last thing, which is the features for immutability. So the theme really for C# 9, if it's going to have a theme, is records and the ability to work with read-only data. But first, we'll start with all the general new features. I've divided them into 4 categories. We've got the general features. Niche features really are fairly specialized scenarios you won't use so often. There's micro-optimization features, which are extremely specialized. It's very unlikely that you're going to need those in day-to-day programming. And finally, the features for immutability, which are this is probably the most important part of it. So at the end, we'll probably have time for questions, so we'll answer some questions to see how we go. So we'll start with the general features. Target typed new expressions. So I'm going to give these demos in LINQPad. So if you want to download all of these samples yourself into LINQPad, you just go to the bottom of the samples tab, click download, import more samples, scroll to the bottom, and choose this one here, samples for what's new in C# 9 Webcast, and then you'll get exactly what I've got here. So let's go back to 2007, before C# 3. This is the kind of code we had to write. We had to, if you want to initialize a new object like a string builder, you basically had to repeat that twice. You put string builder SB's new string builder. And in C# 3, they introduced the var keyword, implicit typing, so we can now replace that first string builder with the var. C# 9, they've introduced another way you can avoid this repetition. We can now do this. You can put string builder SB equals new and leave out the string builder. Now, interesting question. For a start, what if you want to pass in arguments? Well, that works too. You can pass in a string, you can put a string in here to construct a string builder, and that works. We can print that out. And the second question is, what's the benefit in this? Like, why would you want to use this shortcut rather than implicit typing? And the answer is that it's not always the case that the declaration and initialization are in the same place in your code. So here's an example, a very typical example. We have a string builder, which is a private field in a class, and then in the constructor, we initialize the string builder in here with the value from the constructor. So what we can do now in C# 9, we can just delete this string builder. And we get the same result, and that just saves a bit of noise from your program. Right, another example is when you're calling a method. So we've got a method here called printLength, prints the length of a string builder. We're calling printLength, and I'm constructing a string builder on the fly. So in this instance, we can just delete that, and it will work. And to give another example, this one here, I've got a method called gets the distance between 2 points. So the point comes from the WPF Windows system.windows namespace. So I want to get the distance between 2 points. That's the formula for doing it. And I'm calling it, and I'm constructing 2 points in here. So again, we can just delete those points from there. That's now noise now in C# 9. So again, we can basically each version of C#, they're trying to allake it so that you've got more and more code and less noise. So that's a simple feature that helps with noise reduction. Now, you notice with these that all of this code, because it's in LINQPad, we're not having to wrap it in a static void main method, and we're not needing a program class to wrap it in. Normally what you would do in Visual Studio is the simplest kind of program looks like this. You're using declarations, you have a class, you have your static void main method. Right, now, that also works in LINQPad. You can do it like that if you want. But more commonly, this is what you'll do. You'll put in just console. You just put the meat of the program, and you can leave all the noise out. Optionally, you can put using directives in here. With LINQPad, it automatically imports the commonly used namespaces. So this is actually line is redundant, but we can put it in if we want. Now what they've done in C# 9 is now this is actually valid C# 9 code, and you can paste this into Visual Studio. So I'll demo this. We'll we'll go into Visual Studio and we'll create, it's a bit more work than LINQPad, we'll create a new, this is a new console app. Console app 2, that's it, create. Here it is. Now what we can do, I think we also need to check what we're targeting here, which is not the latest framework, to change that to 5. Okay, build that, make sure it works. Okay, so what we can do now is we can delete all of this stuff here. We can just basically get down to the console.write line. So run this, and that works. Right, this feature is called top level statements. Now another thing we can do, if I just go undo all that and we go back to this, you notice that the main method can optionally accept args in there. So I can put console.write, for instance, args.length. So these are the command line arguments that are passed to it. So if I run that, I'll get 0 because I'm not passing any arguments to it. This still works if I delete all of this noise and just put this in here. That args is still magically available, so this will still work. And we can also return a value to the command line, so I can return a number like 1, 2, 3, and again that's going to work, that will compile and work fine. So that's the top level statements feature. Now I'll go back to LINQPad because there are a few other features that are important to this. One of them is that you can define methods in a top level statements program like this. Now these methods, they implicitly become local methods because the way that the compiler deals with top level statements is it takes all of this stuff here and it wraps it inside a main method and it wraps that inside a program. So it turns it back into that stuff we had before. So that means that when you put a method inside another method, it becomes a local method. And a consequence of local methods is that you can access the variables that are declared outside the method. So if I declare a variable here in our top level program such as message, and I call then say hello on that, we can access that. So I can run that and that'll work. It will show hello world in here. Now a nice feature of top level statements is we can add class and namespace definitions after the top level code in the same file. So after I've got a class now called greeter with a static void method say hello, I can call that. That works. And I can even define namespaces I can even put namespaces in that same file after this top level code in there. Again, all this works in Visual Studio. I can copy and paste that in. That works. I'll run that. Right, so now one thing you have to be, that's probably fairly obvious, but something that's probably worth mentioning, is that we can add as many more files here as we want to the solution, to the project. But only one of them can have top level statements because there can be only one entry point in the program. So I'm going to go back to this one here. And I'll go back to the one that captures this variable here. Take that one, paste that one into Visual Studio. There it is. So what I'm going to do is we'll have a look. We're going to disassemble that and have a look at what it looks like in IL Spy. And just to show we're not cheating, I'm actually going to open up the one in Visual Studio. So that would be in Console App 2. And let's have a look see what that looks like when we disassemble it. See how these top level statements actually resolve. So you can see what it's done. It's created a static class called program with some extra symbols there, and it's created a static void method called main, and it's wrapped all that stuff inside that static void method. So you can see this is why this has become a local method. Okay, so let's move on to the next feature, which is covariant return types. It's a fairly simple and cool feature. So this is what we had to do before C#9. So what I've got here is a person class, has a name, and I've written a virtual method which clones the person. It creates a copy of that person with the same fields in there. Now here I've subclassed that to a student, and I've added an ID field. Now I need to override that clone method so that it clones the student rather than cloning the person. So it creates a new student and assigns the name and assigns the ID. Now this all works. The only problem is that when we override it, we have to return a person because this is what we did in the base class. So that means that when I call the student clone method up here, I need to cast it back to a student before I can actually use it as a student. And that's not a very good situation. It's a bit of a wart. Now there's various workarounds you can do. I mean, one of them was something like this, where you create a protected method called clone core or clone internal, and then you create a public method which calls that, called clone, and then in the subclass, when you override it, you override it to clone the student, and then you use this new operator to hide the old one. So we create a new method called clone which hides this one in person. Right, so with this one, we no longer need to do a cast in here. So this kind of solves the problem, but it's really ugly. Now, what we can do in C#9 is really easy. We just go back to this old code and we replace person with student. So we can now override a method such that it returns a more specific subtype, a more derived class, and that works fine, and we no longer need to put the cast in here. Now, this is a feature I think is long overdue. Right? To me, it doesn't make any sense that you shouldn't be able to override something with a more specific type, because if you look here, the contract is the clone method must return a person. Now, what we're doing here is we're returning a student which is a person and more, so it can never really break anything by returning a student here. So that's a simple feature, and they've basically taken away a restriction of the when you're doing overrides. Now the next new feature is local function attributes. So you now have the ability to attach attributes to to local methods. So in the past there was a kind of weird rule which says you're allowed to attach attributes to methods unless they happen to be local methods, and then we don't allow attributes to be attached. So now they've relaxed that restriction, and the reason I believe they've done that is because all the methods that are declared within top level statements are they are local methods. So otherwise you couldn't apply attributes to local to methods in a top level statement. So this is an example of where you might use it for unit testing. Now the next feature they've added is a whole bunch of improvements to pattern matching. So here's a really simple bit of code. We've got variable x, which is 3, and I'm asking to dump out whether or not x is greater than 2. So obviously 3 is greater than 2, so that'll return true. But now what we can do is, instead of putting x greater than 2, I can put x is greater than 2, and that works. Now it doesn't look like we've really gained much here, right? But something a feature of patterns is you can use them after the is keyword, but you can also use them in switch statements and switch expressions. So here's an example of where we can use this now in a switch expression, this function here. So we can now use the relational operators, less than, greater than, less than equals, greater than equals. We can use these in switch expressions, and now it becomes more useful, at least to a degree. Even this isn't really that useful, because we could actually accomplish the same thing using the ternary conditional operator, right? So you might say, well, I prefer one versus the other, but there's not really a lot of gain going from that to this. So question then is what is the point of this relational pattern? And I believe the idea of this is when you use it in conjunction with other patterns. Now, another pattern they've introduced are the combinators. So what you can do now is you can put, going back to this earlier example, you can say x is greater than 10 or less than 5. All right, so that will return true. But I can keep adding more things on here. X is less than 10 or greater than 5, or it's equal to 100. All right, so if I put 100 in there, it will be true. So here's some examples of where we can use that in a more practical way. So this one is val, will tell you if a character is a val. So I can say if C is an A or an E or an I or an O or U. Now the obvious benefit here is we're avoiding repeating this C. We're not saying if C equals A or C equals E or C and so on. So we're having to avoid repeating this thing here. This one here tells you returns true if n is between 1 and 9, uses the less than equals. And is letter, this one here tells you if it's an upper or lowercase letter. And this one is using the and the or operators. Now when you're using the and the ors and the nots, the standard precedence rules, the same one that applies to the logical operators applies here. So and has higher precedence than or. But if you want, you can insert parentheses, and you can do this for two reasons, either to change the precedence, or if you make it clear what's going on, right? So I can add some, this won't change the functionality, but it will make it clearer. So I can add parentheses here, and then this here has this, it's kind of cute. It saved us a little bit of code using these patterns. Now you can also use the keyword not in patterns, and the not solves a particular problem, which is this one here, where you've got something, say, of type object, or maybe it implements an interface or something, or a base class. And how often have you ever encoded like this? If not x is string, right, and you print something out. So this prints out not a string if x is not a string. Now we can change this now to if x is not string. Now we're not saving any characters here. In fact, we've added a character, but it just looks nicer, and I think that is a kind of a nice feature. But there's also something else we can do here. Just make sure this works. We can say if x is not string s, we can introduce a variable. So if it's not a string, it assigns it to s. Then I can say s equals foo. Then s is definitely assigned at this point. Right, so now I can dump that out. S is now in scope because it's definitely assigned. So that's kind of a nice feature as well that they've added. So they've got some effort here in looking at the definite assignment path. So that pretty much wraps up the general new features, the relatively simple ones in C#9. We're going to look next at the niche features, the ones you use more rarely, before going on to the micro optimization features, and then the main benefit, which are the immutability features. So we'll start with the lambda discards. So with this one now, I can whenever you use a lambda expression, you can use the underscore as for an argument. Now this worked before, but it was actually an underscore symbol, right? But now underscore means a discard, so it literally ignores that. So what this does now is I'm using LINQQuery to replace all these characters with asterisks. Question is really what the benefit of that is. Well, there is no benefit in this particular case, but if we were to call another overload that said it has two arguments, I can use an underscore for both of them. So this works. Well, before when this was a variable rather than a discard, you'd have to do something like this to make it work. Right, so now obviously we can get rid of that noise and we can just use the underscore. That's a minor feature. It's not often you're in a scenario where you're going to need that, but it's there if you need it. Next niche feature, module initializers. So what you can do now is you can define a method that will execute once when a module, which effectively amounts to an assembly in .NET Core, when that assembly is first loaded up. So to do that, you define a internal or public static void method, and you add this attribute to it, this module initializer attribute. This will execute the first time once when that loads up. So there it is. So I'm running that now. Because LINQPad preserves the same process between executions, so you can kind of cache stuff. If I run this again, this module initializer will not run on subsequent executions. Now, question is, why would you use this? Because you can achieve much the same goal with static constructors. But there is a couple of advantages. Like one of them is this can be useful if, let's say, you want to do some some complex assembly resolution logic you want to add to your assembly so that it can help resolve other assemblies. You want that to run no matter what type you access. This is a kind of cleaner way of doing it. Bit of a niche scenario. And the other one is that it can be considered a micro optimization as well, because static constructors have a little bit of an overhead. Because when you think about how they work, every time you access a member of a class that has a static constructor, the CLR needs to check to see whether the static constructor is run or not, and if not, runs it. That adds a little bit of overhead. So this way you're getting rid of that overhead. Okay, the next niche feature is for each extension methods. So what you can do is you could define an extension method called getEnumerable on any type you like. Now, sorry, getEnumerator. Now, this method, if any type defines an instance method called getEnumerator that returns an enumerator object, you can then use a for each statement on it. But now, for a type that doesn't define such a method, you can define one as an extension method. So you can make any type amenable to the for each statement. So in this example, I've made the integer type now amenable to enumeration. So we can do for each over an integer. I can put for each int I in 10. I.dump. So that's kind of like a for loop now I've got, but with less code and less noise. And this might be a kind of useful extension that you might want to use. And it's a fairly low cost feature, and it's got some at least niche applicability. Now, final feature in the niche one is called extended partial methods. Now, I'm not really going to go into this. I'll leave this here so you can look at it, because this feature is really intended for a single scenario, which is C# source generators, and that is a whole presentation in itself. So if you're interested in this, look up C# source generators, and then this is where this particular feature will come in use. So we're going to move on to micro optimization features. These are the ones you will almost never use, but it's good to know they exist, just in case you should run into a scenario where you need them. You can look it up. You know that these options are available, but very rarely will you actually need these in practice. Now, first one is static lambdas. Now, what you can do with static lambdas is you can put the static keyword before a lambda expression. This has no effect on the IL. So if we look at the IL this produces, if I remove the static keyword, nothing changes. It does exactly the same thing. So what this does, though, is it prevents us from capturing variables. So if I say put string s equals exclamation mark, I could put select c becomes char.toUpperC plus s. I'm appending this exclamation mark onto the end of everything. Right, so if I run this now, we're going to end up with all these letters with an exclamation mark after the end. An exclamation mark comes from this variable s, which we've captured. Now, if I put a static in here, it will prevent this from compiling. It will give us a compile time error saying you're not allowed to do this because you got static in there. Question is, why would you ever want to do that? Why would you want a feature that stops you doing something potentially useful? And the answer is that one of the extreme micro-optimization techniques that they use inside the CLR and inside real performance hotspots such as the C# compiler itself, the Roslyn compiler, one of the techniques you can use to make things really fast is to minimize the number of allocations, memory allocations on the heap. Right, so whenever you capture a variable like this, when we're capturing s, this requires heap allocations to deal with it. We need to create a class to create a closure to capture this. So that has an effect on potential effect on performance. Now, one of the techniques you can use is in performance hotspots, you can very carefully write the code such that it does few or no memory allocation, so it puts no load on the garbage collector. Allocations are generally cheap, but the garbage collection later is more expensive. So if you can avoid allocation, you avoid garbage collection, so you can make things run really, really quickly, low latency. This is an extreme micro-optimization technique. Now, if you've gone to a great deal of trouble to make this code hot path completely allocation free, you don't want to have a trap whereby later on another programmer goes up to your code and does this and captures a variable, not realizing that they're breaking your performance optimization. They're creating a memory allocation by stealth. Right, so by doing this, you're saying to any subsequent programmer that works on this, including yourself in a few months, please don't capture anything because I'm trying to make this an extreme performance hotspot. Right, so that's basically what we're trying to do with that. Now you can also use this with local methods. So if I put static, if I create a local method, string foo s. I'll just make a very simple method that returns the same thing. If I can put static in front of that local method, and that will also prevent that from capturing anything else. It's probably a bad example to use s there. I should probably use something like, we'll use x. Right, so if I was to put in here s, again, that's now going to fail because of that static in there. Right, static local function cannot contain a reference to s. So you can use this as well on local functions to make sure they can't capture anything. Again, this is not something you'll use very often. Next feature, which is probably even more specialized, is function pointers. Now, function pointers, it's like a unsafe version of a delegate, right? A version that bypasses runtime type safety. Now, function pointers, they're very restrictive in that they can only refer to static methods. You can only point them to a static method, not an instance method. That restricts their usability. In this instance, I'm pointing it to the getLength method. We use the ampersand symbol to get a pointer to a method, and you reference the type, the pointer type, by using delegate star, and then using the angle brackets to reference the types. Right. So this means a function that takes a string out and returns an integer out. So this function here takes a string in, returns an integer out. Now this has static type safety, because if I change this to something like double, right, that's not going to compile, right, because that type doesn't fit this type here. So we get static type safety, but we don't get runtime type safety. We can do a cast at runtime to cast that to something else, and just things can blow up in a horrible way. So question is, when and why would we use it? The obvious answer would seem to be it gives us a performance advantage. So we'll run this one here. Right, this gives us we're getting the getLength function, and we're calling getLength on this string, returns 12 characters. And this here demonstrates that the function pointer is not an object like a delegate. A delegate is an object. It's a class. And it's an instance that lives on the heap. This is just a number. It's just a pointer to memory. Now, in order to appreciate the performance advantage of something like this, there's really only one way you can know, and that's by doing a benchmark. So the way to do it, to do proper benchmarking, is to use a NuGet library called benchmark.net. So in this query, I've got a NuGet package reference to a library called benchmark. This is the standard for doing benchmarking. This is all sorts of things you would never think of doing yourself if you wanted to do benchmark. You can get genuinely accurate results. So what you do is you create a class and you annotate the methods you want to test with the benchmark attribute. So I've got 3 methods here. I'm testing a delegate, an ordinary delegate. I'm testing it with a function pointer, and I'm testing it with a direct call that bypasses. It just calls a method directly. This is the method we're calling, a very simple method. Takes a single parameter and increments an object. Right, the simplest thing we can do. And I've got this attribute to prevent it being inline, so we know that the method call is actually happening. So what we're going to do is we're going to use benchmark to run this test just to compare the performance of the delegate with a function pointer and a direct call. So let's see what happens. Right, this will keep doing more and more iterations until it gets a stable result. Okay, so these are the results. It's giving us the results in milliseconds, but notice that we're repeating each one 1,000,000 times. So this is actually nanoseconds. So to do a direct call is 3 roughly 3.5 nanoseconds. With a function pointer, it's almost the same. And with a delegate, it's 4 nanoseconds. So what we're saving with a function pointer is half a nanosecond per call. Right? That is so small, it's really not going to amount to anything. So that leads us to the question, like, what's the point of this feature? And the answer is that function pointers have got another trick up their sleeve, but it's even more specialized, and that's when it comes to interop. So what you can do is, if you're using pinvoke to call an external C++ function or a Windows function, you can use function pointers for that too, as long as you're happy to point it to a static callback and not an instance method. So as long as you've got a static function which can service your callback, I can call this Windows WinAPI call method called enumWindows, which it basically goes through all of the window handles on the machine, and it calls back with each of those Windows handles. So I'm going to run this now. This gives me all the handles of the windows on this machine, and rather than putting a delegate here, I'm giving it a function pointer. So then it calls this function here, which dumps out the window handle. Now, what's kind of interesting is that this hasn't really saved us much either in terms of performance, but there is something you can do, which is you can apply this attribute called unmanaged callers only to the callback. Now, if you do this, you cannot call this method from managed code. You can only call it from unmanaged code via a function pointer, and then it can take some genuinely useful shortcuts, right? So what it can do is effectively it can short circuit some of the overhead of the transition between unmanaged and managed code. So with this, apparently you can get some good benefits, but this particular example, it will not really show it off because this function itself is very slow, right? So you need a function that's incredibly fast itself to execute in order to measure the improvement in the calling convention overhead. So again, good to know this is here, but you're almost certainly not going to use it. The next one is locals, skip locals init. So here's we've got an unsafe method. It declares a local variable, and a pointer gets a pointer to that local variable, prints it out. Then it does a stack alloc, which allocates 20 integers on the stack, and it prints them all out. If I run that, we're going to get all zeros because the CLR has a policy of initializing all local variables to 0. It clears them all out to 0. And this is, I believe it's probably existed, that they're probably thinking about security in the days of code access security in .NET Framework. This kind of stuff made sense to help prevent mistakes. But when you think about this, we're in an unmanaged environment. Like if we were to do a stack alloc on that, it's very likely we're going to want to populate all of that memory ourselves. So what's the point of initializing it to 0 and then populating it again? A little bit of a waste there. So what we can do in C#9, we can add the skip locals init attribute, and that tells the CLR not to do that initialization to 0. So what that means now, run that, it's going to, in this instance, because we're not initializing it ourselves, it's going to print out some uninitialized memory if this works. And that's indeed what's happening here. It's printing out some random uninitialized memory. So again, now in terms of performance gain, it's measurable when you're doing large stack allocs, right? If you simply had these 3 lines here, you're probably not going to notice a difference, but with large stack allocs in a performance hotspot, this can improve performance. You can apply this attribute to a method or a class or a whole assembly, so that the whole thing has this skip locals in it, and it has no effect on safe code, because C#'s definite assignment policy prevents you from accessing uninitialized memory anyway in the safe context. So this is really relevant to unsafe stuff. Now finally, another final micro optimization feature, are native size integers. Now this is a bit of a strange feature because they've introduced 2 new numeric types called nint and nuint, and nint is a native size integer, nint native size unsigned integer. So this will either be 32 bits or 64 bits, depending whether you're on a 32-bit platform or a 64-bit platform. Now that is exactly what int pointer and uint pointer do. And in fact, if we run this code, or run this code here, you can see that they're actually using the int pointer and uint types to implement nint and uint. So it looks like these types are identical. That nint looks like a synonym for int pointer. The same way that int, right, is if I put type of int, type of int32, right? It seems like basically this is following in the same footsteps, but it's not, right? This is where it's confusing, because while these types are equivalent at runtime, they're very different at compile time. nint at compile time behaves differently. The compiler does some special magic. You can think of it as wearing a different hat. It's the same type, but it wears a different hat. When it's cast to an nint, it has a numbery hat. It allows for numeric operations. Like we can assign numbers to it, and we can do multiplication, addition, subtraction, and so on. We can do the shift left, shift right operators on it. It's intended for doing numeric operations on a type whose size matches the address space that we're working in. Now, what this means is if you're currently using int pointer and uint pointer for handles, for interop, you should continue doing so, because you shouldn't simply switch to nint, because all it will do is, by switching to nint, is going to allow you to perform pointer arithmetic, which you almost certainly don't want to do. So if you're working with handles, stick with int pointer, right? But if you actually want to perform numeric operations, that's when you will want to use these types. So the question is, when on earth would you want to perform numeric operations on native size integers? And the answer, it's highly specialized. And again, it's in the micro optimization domain. It's when you want to essentially do arithmetic on addresses, right? At pointer arithmetic. So an example here is if you look at how the this helper method is implemented. There's a helper method called memory copy. So this basically copies literally memory from one place to another. And if I F12 on that, I'll look at the definition, how that's implemented. This calls a method called memmove. If you look at how that's implemented, it makes heavy use of this, right? So if you're going to write your own memmove function, right, having this native size integer stuff, this is kind of useful. But outside of this context, it's something you're probably never going to use. So we're gonna finish up now with all these features that you're not likely to use, and we're going to go back now to the crown jewel of C#9, the features you're likely to use, and that is the features for immutability. So there's two of them. The first one is init-only setters. So what immutability is its ability to create types that you can't change, whose fields or properties cannot change after they're created. And this really helps with functional programming, and it helps make programs more easily parallelizable and work better with concurrency. It's a very popular pattern, and it's a pattern used by the Roslyn compiler itself. The C# compiler makes heavy use of this. So let's look at how we would traditionally write an immutable class. Here's one called, I've written a class to represent a note. So this one has a pitch and duration. What we would normally do is we create a note, we have a constructor, we have, it takes those two parameters and it assigns them to two read-only properties. So once we've created a note, we can't change that, we can't modify it. So that's pretty simple, it works well. It works very well when you've only got two parameters, two properties, but what happens is you start adding more and more parameters and properties to it. It gets messier and messier, because you have to, whether they're mandatory or optional parameters, they all have to appear in the constructor. So here's an example of how bad it can get. This is a type from the Roslyn compiler. So look at the NuGet references. I'm referencing Microsoft Code Analysis.C#. This is the Roslyn compiler. When you want to do a compilation, you need to create a class called C# compilation options. Let's look at what the constructor looks like. That's how many parameters you have. Now, the first one, you notice, that's mandatory. You have to specify an output kind. All the rest are optional. And that's very common. When you've got here 27 parameters in there, it's very common you have one or two or three mandatory one and all the rest are optional. But because this is immutable, that all of those have to be fed into the constructor. And this is not a nice experience to use this. And there's another problem with this too, which is that you can see there's 6 overloads there. And what happens is that when they first released Roslyn and they wrote this, they didn't have all of those there. They had maybe half, 2/3 of them. And then each new version of Roslyn, they add 1 or 2 more optional parameters to this. And this is a very common requirement. You know, you keep adding more features, more options, so you add more of these parameters. Problem you get is, let's have a look at how this works. So let's say I want to add 2 optional parameters, volume and channel, to there. So I've created two properties. I made them nullable because they're optional. I set default values for these. Now imagine that I release this previous one. I published this in a library. I released it to NuGet. Now I come up with this new version with these extra 2 parameters. I published that to NuGet, a new version. Problem is that this breaks binary compatibility. So any code that was compiled against this older version will crash if it's run against this newer version unless it's recompiled, right? Because we've changed the number of parameters in the constructor. This is a binary compatibility problem. I can go into more detail on this if you're interested. You can post a question if you're interested, and I'll go into this as to exactly how this happens. But this is a big problem. So to work around this, what you have to do when you want to release a new version is you have to leave that old constructor in there, right? But you don't want it to appear in IntelliSense, right? So you get too many overloads that are confusing. So you add this attribute to hide it from IntelliSense, right? And then you there's a new one. You write your new constructor with a new one, and then you call the old constructor in there. Now, each time you release a new version and add more optional parameters, this gets worse and worse. So it's a pretty bad situation. So what we really want is we want an experience similar to what we would get if we had mutable types. So imagine that we said, look, let's abandon immutability. Let's just not worry about that. The situation will be a lot better, because what we could do is we could have our constructor just take the mandatory properties, these mandatory arguments, and then we can add these optional ones in purely as properties, right? So when you construct it, you pass in the mandatory ones, and then any of these optional ones you set using an object initializer. Right? This is a much nicer experience, right? We've created now. We've got rid of the versioning problems, and the thing is much nicer to use. The auto-completion listings look much nicer. If I hit Control Space, I just get the ones that I haven't set in here. This is really nice. The only problem is we've broken our immutability. So is there any way that we can eat our cake and have it? Can we do this, but make it immutable? And in C#9, the answer is yes. All we do is replace this set with an init. What that does is that works fine. You're allowed to set these in the object initializer like this, but as soon as that object initializer has completed, it now becomes immutable. So I cannot alter the channel now. If I try and increment that, I get an error. So we've created immutability without needing to have a constructor with dozens of optional parameters on there. So basically that's how, these are called init-only accessors, is how they work. They can be initialized via an object initializer, but nowhere else. Now there's 1 or 2 other places we can do this. So one thing I should mention before we proceed is that these are automatic properties, right? So it's automatically writing the accessors for us, but if you want, you can also write the accessors yourself. So in this instance, with this channel, I've defined my own backing field, and I've written my own get accessor to return the channel, my own init accessor to assign the channel. That works too. It works just the same. You're allowed to do that, and that's advantageous when you want to put validation logic into your init accessors. That can be useful. But here's what's interesting. You notice in the init accessor, I've set the channel to the value here. I'm assigning this, and yet this is read-only. Right? You're allowed to do this in an init accessor. You're allowed to assign a read-only property, and this is essential because if it wasn't for that feature, if we had to make this writable, this is no longer really immutable now, right? We can still modify this from the inside. A true immutable type, everything has to be read-only, right? So this allows us to have 100% immutability, this feature, the fact we can have a read-only field and we can set it from the init accessor. Now, the only other thing that's left now, we've solved this problem nicely of this horrible burgeoning constructor. But when you've got an immutable type like this, what happens when you do want to modify it, right? So let's say I've created that note with this pitch of 20, and I want a new note with a pitch of 21. So what you need to do is you don't modify the existing one, you create a new note that's got all of the same properties and fields, but with that field that you want changed. So to do that, you typically write these helper methods. So what we would do in the past is we'd write these withers, these methods that start with width, with pitch, with duration, with volume, with channel. So what this does, it takes a new pitch and then it creates a new note which incorporates that change into the new value. So by doing this, we're not altering the original one, we're creating a new one that incorporates a modification. Now, there's an obvious problem with this. There's two problems with this. One is that if you want to modify two properties, you've got to call two with methods, and that's inefficient because we're creating two copies. But the other thing is that writing all of these methods, that's a lot of work, right? That's not fun. And there's yet another problem with this, which is that we can't subclass this. If we were to subclass note, all these methods are broken because they're going to return a new note and not a new subclass note. Right? So this is not amenable to subclassing. So we've got three problems with this approach. It's pretty nasty. So this is something that they're fixed in C#9. So C#9, I can delete this and I can turn this from a class. I put a record in there. Right? So now I also need to make sure that these properties here, if I want to non-destructively mutate, then it's called non-destructive mutation, what we're doing. So now what I can do is, instead of calling with duration 200, I can put note with duration equals 200. Right, and now this will work. So what this does now, it creates a new note with a duration of 200. The original note is still unchanged. Right, so now I've got the ability to do non-destructive mutation without any boilerplate code. And this is also, records are designed to work well with subclassing. It works perfectly with subclassing. And we can also have we can non-destructively mutate more than one property, so I can mutate the volume as well. And there, run that, and now I've got the volume has been set as well. So records, the main purpose of records is to allow for this non-destructive mutation. But it's not the only purpose. There's a few other benefits too. I mean, one of them is that in simple cases, you can cut a lot of noise. So you notice in this instance, look at the word pitch and duration. How many times does it appear? Once, twice, 3 times, 4 times. There's a lot of noise here. This constructor doesn't have anything novel or interesting. It's doing really basic kind of repetitive work. Now in these simple cases, we don't have any kind of validation here. What we can do is we can take the constructor parameter list, cut it from there, paste it into here, and we'll change this to uppercase to match how we want the properties. And now what we're going to do is we can delete this constructor completely, and we can delete these properties completely. And we're going to get exactly the same result, right? The compiler will automatically generate that constructor, and it will generate those init-only properties to get to the same effect. So we've cut an awful lot of noise out by doing that, right? Now this only works in simple cases, because as soon as you want to add argument validation, which so often you do, right, with non-trivial stuff, you obviously use a shortcut because you need to write your own init accessor to do that. But simple cases, you just want a bunch of values and connect them together. This works quite nicely. Right, there's something else you can do too with this. So what I'm going to do now, I'm going to create a couple of notes, note 1 and note 2. Now what happens is note 1 equal to note 2. Are they the same thing? They've got the same values, but they're different objects. So are they the same or different? It turns out that with records they're the same. Right? If this was defined as a class, they would be different because they're different objects. But the thing with records is that they implement what's called structural equality, which is like structs. Right? Two objects are the same if their values are the same. If all of the values of their members are the same. So this gives us structural equality by default. That's a nice feature. And The final nice feature is I can go note1.toString. If you call to string on a record, it gives you, formats it nicely like it does with anonymous types and tuples. So that's records in a nutshell, but I'm going to go into a little more detail in exactly how they work. So what is a record exactly? A record effectively, I'll collapse this stuff, a record, it's a class with extra compiler added go. Compiler adds stuff to it. So here's the first thing it does, if you define a record, is it looks to see have you defined a parameter list. Right? If you've defined a parameter list, the first thing the compiler does is it expands that parameter list by writing these init-only properties, and it writes what's called a primary constructor, which takes those as parameters and populates them. It also writes a deconstructor for you, which is also sometimes useful. So still at records, so it takes that record and it expands those that parameter list first. The next thing it does is it converts this into a class. So to do that, first of all, it includes all of the code that's in that you've put inside your record, and you can put pretty much anything you want in there. It just puts it in. You can put any extra methods or operators in there, and you can even, if you want, you can add mutable fields. I mean, while records are designed to work for the needs of immutable types, you don't necessarily have to make them immutable. If you want, you can put mutable stuff in there. So now the next thing it does is it adds some members to implement that non-destructive mutation. Then it adds members for that structural equality comparison. It overrides the equals in the get hash code. And then finally, it writes code to do the toString. So I want to look at the code it does for non-destructive mutation. It's kind of interesting. It does two things. It creates what's called a copy constructor, which takes, it's a protected constructor that takes another same typed object in and then populates itself based on all of the fields and automatic properties in this other object. So what it does, when it creates this copy, it looks at all of the fields, whether they're private or public, and any automatic properties which don't have an explicit backing, again, private or public, and it copies them all over. Right? So it takes a faithful replica of that object. The other thing it does, it creates a public virtual method called clone, which calls this protected method. Right? It does this so that it can override it if you subclass records, because you're allowed to subclass records. So the little slight nuance to this is it's not actually called clone. It calls the method angle bracket clone angle bracket $. Right? We're not allowed to do that in C#. We're not allowed to write a method called that to use those special symbols ourselves, but it does that so that you can't call the clone method directly. Right? You cannot do what we did and create a record by writing a class with the right pattern. You actually have to use the record keyword to do this. That's the only way you can get the clone have those special symbols in it. So what happens? Let's see what happens when you call this with method. The first thing the compiler does, it calls this clone method, which calls the copy constructor. So it creates a faithful replica of the object, and then it goes to this initializer, and then it calls the initializer, these init accessors, to update that copy of the object as requested in here. That's essentially how it works. Now this copy constructor in here, right, this clone method, you can't see that, you can't explicitly interact with it, but this copy constructor, you can take that over. If you are not happy on the way it wants to write the copy constructor, you can write your own. So here's a very simple example. I've got a record which with a parameter list, and I've written my own copy constructor. It's got the right signature, the same signature, so it will use this one instead. Right? So I can run this and I'll get the same result. And if I stick a breakpoint in here, the breakpoint will stop, so I can see it's actually calling it. Right? And this can sometimes be useful, being able to write your own copy constructor. Now, one of the common requirements of any type really is to have argument validation. Now, as soon as you want to validate the argument, you can no longer use this parameter list. You have to write out the properties in the constructor explicitly. So here's an example of where we're doing it. So I've created a pitch property. I've noticed there's no parameter list anymore. I've created an explicit init only, and I've also created a duration property with a backing field, and I've written an init accessor, and in this instance I'm only allowing this to work if the value is greater than 0. So if the value is less than or equal to 0, I'm throwing an exception here. So I'm doing basically the property validation here. So when I instantiate this, I instantiate a good node, it'll work. If I instantiate a bad node where I'm putting -1 into the duration, this will throw an exception here, right? So duration must be 0, and if we'll break on the exception just to see the stack trace in there, and you notice it's being called from the constructor, which is being called from here. So effectively, when this constructor tries to assign the property, it's going to go to the init accessor and fail. Right? But the other thing is, if I comment this out, if I create a good node with valid arguments and then I try to non-destructively mutate it with an invalid argument, it's also going to crash. This will also work, right? The stack trace is a bit different now. So if we have a look at this, what's happening is it's calling the init accessor here from this code here, from there. So again, this works. So no matter what the scenario, if you put argument validation logic into your init accessor, it's going to work. It's going to protect you. Now, let's look at another feature which you may wish to add to this, which is the ability to write calculated properties. So in this instance, I've got a property called distance from origin, which tells us how far this is from the 0 point using this formula. Now, this is relatively cheap to calculate, but we can just imagine this is a more expensive formula, so it's going to take longer. So let's say we want to cache this. So rather than calling this formula every time we call this property, we want to cache this and just do it once. Now, one way you could do that is you could write a constructor in here and you could work it out in the constructor. Right? Now, this would seem to be okay, but this doesn't work with non-destructive mutation, because you think about what happens if we non-destructively mutate this, we change, say, y to 10, then what happens is it calls the copy constructor, which creates a copy of it. Then it will call this init accessor to update these values. So the problem is this distance from origin will still be the old value. So in this instance, this non-destructive mutation, when I run this, even though I've updated now the y to 10, I'm still got the same distance of origin from before. So you have to be a bit careful on how you deal with calculated fields in here. So the other problem with this is that we're incurring the cost of this formula whether or not we actually use it, whether or not it's called. So the better approach to do this is to have a lazy field. Right, so what we do now is you define your distance from origin, you write up a backing field of a nullable type here, and you say if it's null, then work it out, right, and then return the value. So this way we only calculate it once the first time we access it. Right? Now, this solves the efficiency problem, but again, this isn't gonna work. It doesn't solve the non-destructive mutation problem. To solve the non-destructive mutation problem, we need to modify the init accessor so that whenever these values are modified, we clear out the cached field, right? We clear out the distance. So when we do this now, this will work. So when we change one of these x or y values, it clears out the distance from origin so that next time we access it, it will recalculate it. So now this will work. Now the distance from origin will now update itself. Now, the only kind of problem I'd say here is it's a bit noisy. There's quite a lot of code. But they've introduced a feature in C# to C# 8 to reduce this a lot. So all of this code here is pretty noisy. What we can do now is we can basically delete all of this. Right, we can use an expression body function, delete all of this here, and use this one here, this function. So what this does, this is called the null coalescing assignment operator. This was introduced in C# 8. And this says, evaluate to distance, but if distance is null, do this computation and then assign it to distance. Right? So if distance is null, it evaluates to the right hand side and it assigns it at the same time. Right? So with this now, we've got straight away we've reduced the number of the lines of code quite a bit, and there's something else we can do. Else we can do to reduce this, which is this constructor here. We can use a shortcut. So rather than assigning x and y separately, what you can do is use, again, this is features that were in C# 8 and 7. What this does, it creates a tuple with x and y, and what this does is it deconstructs the tuple into the x and y properties. So this is a nice little shortcut you can use to write constructors when you're assigning those variables. So now we've reduced the number of lines, we've got rid of most of the noise. This is relatively clean. It works very efficiently with computed properties. Now, there is one other way you can handle this. What you could do, kind of clever, what you could do is we could implement it by having a parameter list in here, so it writes the properties and constructor for us, right? And then we could write our own copy constructor, and we can write it such that it only copies over the x and y properties, right? Because without this copy constructor, it's also going to copy over, of course, the cached field, which is what we want to avoid. But if we rewrite this copy constructor now so it only copies over the cached fields, only copies over x and y, this will kind of achieve the same effect, right? It's not quite as efficient as the other method, in that if we were to add other properties to this that weren't affected, let's say we were to add to this, we wanted a string units, right? So I'm going to have in here pixels, right? So I'm going to construct it. I'll put x, y, comma units equals other units. Okay, so if let's say I add units in there. Now I want to mutate it. So we're going to change the units from pixels to EM. Now with units equals EM. Okay, now problem, this will work perfectly well, but the problem is that this will unnecessarily erase this cached field, right, during this this copy constructor. We're not cache in this particular case. The units don't affect this calculated field, so we're unnecessarily losing that cached field. That's the drawback. But if you are going to take this approach, there's another pretty cool thing you can do, which is you can reduce this copy constructor. Instead of putting, we can do it here in this example here, instead of writing x, y, z units equals that, we can just put other. Right, we can. This uses the fact, because when you define a parameter list on a record, it automatically defines a deconstructor. Right, so we'll go back to this record expansion when I first showed how the final translation works. In fact, we don't even have to go that far. We'll go to this one here. So when it sees a parameter list, it translates it into this here, and you notice that it automatically gives us the property declarations, it gives us a primary constructor, and it gives us a deconstructor. That deconstructor allows us to just do this. We can say x, y, units equals other, and it invokes a deconstructor. So that's a nice shortcut, as long as you're happy with that potential inefficiency as in terms of having these calculated fields. So that wraps up the most useful features of properties. A couple of others here which I can go into if you're interested, but the one other thing I'll talk about is equality comparison, because that's something we talked about a bit earlier. So if we create two objects by default, our equals methods and our equality operators implement structural equality, so that returns true. Now, what happens if you want to change, you want to override that equality, because that often happens. And in fact, if we just go to this previous example we look at this example here of how we can implement calculated properties. If we want structural equality to work in this example, it's important we don't include this calculated field, because this may or may not be populated. So the question is, how do we, if we're not happy with the default structural equality, how do you modify it with the record? And the answer is it's relatively simple to do. So let's first look at how you would do it with a class. Like if we defined point as a class, if we wanted to modify the equality, we have to override the equals methods. We have to, ideally wouldn't have to do this, but it's a good idea to implement equitable of point class. There's a lot of ceremony you have to go into this. You have to override the get hash code. You have to create the equality operator and the not equality operator. That's the general, the rigmarole you have to go if you want to do a good job of overriding equality comparison in a class. Now, the good thing about records, it does all this stuff for you. So if you want to fine tune how it does equality comparison, you don't have to do all this. Much easier. All you do is you define a public virtual method called equals, which is strongly typed. It takes the type of the record, and you have it return the correct value for equals, and you override get hash code. That's it. That's all you have to do, and now it will use your equality comparison instead. So we can verify this works by putting a breakpoint in there. It's being called from here. All right, from this equals, and also it's called again when we're using the equality comparison in there. Okay, so I think this is more than an hour, so I'm going to wrap up now. So for more info, I've told you where you can get the samples. There's also C# itself, sorry, LINQPad itself has got a bunch of samples in the what's new in C# 9. That's a more summarized version of what we did. There's also these are the two books that I've recently published. This one's almost should be available within a week or two, and this one will be available in March. C# 9 in a nutshell. So I'll hand back over to Martin, so we can look for any questions or comments. So I can see they're appearing here in a list.
Yeah, I think thanks for that, Joe. I don't know about anybody else, but that was quite enlightening and made me realise how terrible my code is, which is, by the way. So we only had one question that I can see, and we'll just put that one up now. So this was, does that, those native sized integers that you showed, does that not mean that your code then becomes platform dependent?
Well, I think with native sized integers, it would, it resolves at runtime to whatever the size is. So it would help with platform independence of native size integers. It's like similar to with int pointer and uint pointer. It's going to help with independence rather than dependence. Maybe I don't understand the question.
Okay, so if you've got any more details about that question, please type it in, and we'll ask that. Otherwise, I think we'll try and wrap up, conscious of people's time. So thank you, Joe. That was very, very enlightening. Like I say, a great use of LINQPad as well. I mean, it's just such an amazing tool. Now, I did promise that we are going to have some giveaways. So what I'm going to suggest, I'm going to try and share my screen here, just so as we can just move this over here and share that. So we'll just add that. So if you go to the page that is where the actual event is on our user group, so ASLAG is our user group. What I would like you to do, we've got 20 giveaways to give away. The only way I can do this very efficiently is if you type a comment, right? So what I want you to do, I'm going to post this in the comment list over here. I want you to type this into your comment. And it has to be exactly this. And then what I'll do is I'll reach out to each of you who type that. As a user group owner, I can reach out and send you a message, and I'll send you a link and a code, and you'll be able to download some swag. That swag is a t-shirt, it's a mug, and some stickers and various other bits and pieces. So it's definitely worth it. So if you definitely want to get hold of some swag, put that in the comments, and we'll make sure that all gets sorted out. In the meantime, let me just say again, once again, thanks to Joe for such a great presentation, and I urge you to download LINQPad and then buy his book. He's a man who knows his stuff very, very clearly, and we'll try to organise another meetup next month. That will probably be an IT Pro one. We've already got something lined up, and we'll do the same process through YouTube again. So with all that. So I'd just like to say again, thanks for everybody who attended, and thanks to Joe, and see you next time.
Thank you. Thanks for organising it.
No problem at all. Always happy to. Thanks all.